Alright, so this is another example, power and AC circuit. So we're going to go over the problem and then see how it is. So it says a single phase motor, right, is connected to a voltage source, 400 volts, 500 hertz, right, supply, right. It's developing a 10 kilowatts with efficiency. So listen to this very well. It's developing, right? So we should pay attention to this. It's developing. Okay. Efficiency of 84% and a power factor of this lagging, very important, right? So let's go over this single phase. This, so clearly we know that this is developing is for the motor, the single phase motor. It's not for the source. And then this one right here, because it's saying it's developing, right? It's not something that is there, it's now developing it. So that would mean that it's a what's the name, output, right? And because we have watt here, that would mean that it's power, right? Okay, an efficiency of 84, power factor of this lagging, and because it is lagging, that would mean that we are dealing with, what do you call it, a circuit of this sort, meaning we have it to be kind of like, a minute, to be an inductor, right, and in combination with a resistor. This will be a summary for the circuit because it's saying lagging, the power factor is lagging, right? So we want us to calculate the input power. Okay, so let's see input power. So you now to calculate input power. Let's see, are we given anything concerning input key? It didn't just say just power, it just said input kVA. Because kVA is here, that will mean apparent, right? Apparent power. And for us to get the apparent, it's either we'll use, let's see, now for it, we know apparent power. Let's use the symbols. Apparent power symbol S will be composed of just the raw power, and then what do you call it, reactive power, right? But then here's the case, what do we have? Let's see what we have. Do we have any of them? The only power that we are given here is this, which is this one right here is output, right? And it's power, right? So let's see. So what this says is that if you are trying to find the input power, and then we have the output, we are trying to find input apparent power, and we have the output power. That will mean that this particular output here came from a particular input. So we have to find the input. We have to find the particular input first, right? So let's see. Before we do that, so let's see, that will mean that we have to find S input. Sorry, yeah, S input, right? We're given output here. So let's see. We have to find the input. Yeah, we have to find the input first. So that will be power input, right? Because we have efficiency there. So we need power input, right? And we are seeing that we have a power output, which we've been given. And we are always, it's always true that the output is a portion of just the input, because no machine has efficiency of 100. It's not able to convert everything to output, right? So we have the output, and we are saying that it's a portion. Let's make it this way. That is proportional to the P input, right? Okay, right, then so the P out is equal to P in, right? Times efficiency. The symbol is something like this, right? Okay, so let's see, that will mean that we have, let's see, 10, everything is in kilowatts, is equal to this, we don't know, P in, and then we have the efficiency of 84%. That will give us 0.84, right? So that will mean that P in, the power input delivered to the motor, will be 10 kilowatts on 0.84, right? So let's see. So the problem always becomes clearer if you're able to see that this is what you need, right? What do you need to get what you need, right? And you go about it that way, and it makes your work flow, right? So now we are looking for them. We are looking for, what do you call it, apparent power input, right? And then to find that, to actually need just power input, but we don't have power input, but we can find that the power input from the power output, right? So now we are trying to find the power input. So that's 10 on 0.84 on 0.84, right? So that's giving us a power input of 11.90. Let's do 40p, 48 the kilo has not been taken out, right? We didn't introduce the kilo in the calculation, so we're not written kilowatt small k, right? So we have this. So now that we have this, we can go on and find this, right? So because we have the power factor as well. Okay. So then we know P in is equal to S in, I'm just using the symbols, times the power factor, right? So that will mean that S in is equal to P in, that's power input, all over the power factor, right? So let's see what we have. The Pn is 11.9048 kilonewtons, kilowatts, sorry, right? And then the power factor was 0.7 lagging, so 0.7. So now we'll just use the value 0.7. Let's see what we get. 11.9048 on 0.7, and that gives us the power input of 17.0069 what kilo. Wait, let's be careful of the unit, right? So this is power in, that's kilowatt. This is power, but this is apparent power, so that'll be what, kilo VA, right? Volt amperes. Yeah, so that's what we have. So there's the first part solved. That's A. So let's see. The B is asking us to find the active and reactive component of the current, right? So first of all, we know that we have to find what current, right? And then let's see what we need to find current. Have we been given any current value here? No. But then we know that we are going over step by step. Okay. So B, we need current, right? We don't know that. But then we know clearly, very clearly, that we are not going to use V is equal to IL directly. We cannot use that one directly to find the current in the whole circuit. Why? Because the circuit has what is it? Okay, let's see. Because it says some power lagging here, meaning that we have some inductor component and we have some resistor component, right? That's what it says in terms of the power. Meaning that you can't use this one directly, so meaning you have to use V is equal to IZ type. And neither can we use this, right? Why? Because we have the voltage, fine, but we have the voltage. We have the voltage, but we don't have the impedance, right? So let's see. So look at what you have already. You have this. Is there a relation with it to current? Yes. All right. So you can even go back and check with everything I have. But this one, P is equal to I squared R, right? We don't have R, we can't find it. But then always check what you have to see if you can use it to get what you want to get. All right. So we have S, right? So, and in this case, let's see. We need a current, right? So this one is saying that the active and reactive components of the current. It didn't specify whether the input or the output. So let's see. The way becomes easier when you think of it. You think of this just as the input, right? Like, so you're just looking for the input, just the input part of it, the one from the input. Okay, so let's see. Okay, so because we have this, and then there's no other value that we have now to find that, right? So you see, we don't even have a S output, right? Because it says, let's see, it's developing, so we don't have the S output. We only have this, and we use that to find the S input. So let's see, the power input, right? So we know S is equal to, if we are using the RMS values, it's just IV, right? Just IV. But then we have S, we have V, this input, and we have input voltage as well, right? So that's the thing. You must know what you have to get what you want to get, right? So we have S input as well. That means we can find I, and that I will definitely be our I input, right? That will be S input and what? V input, right? And S input is 17.0069 kilowatts, kilovolt amperes. And then this, I think, was 400 or so. Let's see, 400. Input voltage is 400, right? So let's see what we have for that. And then again, let's see. That will mean that for the unit, very important. So let's even put everything there, so we don't get confusing with that. Let's put everything there. Let's see. Okay. So it's safer if you put everything there already. So we know we have kilo here, which is 10 to the power 3, right? Or if you want, you can put the values right there. Okay. So that means we have a 17.0069 on what? 400. And that's what it gives us, right? 0.0425. It can get confusing, especially if you don't notice the k unit given. So at times it's even safer to bring 10 into numbers, like 10 to the power 3. So now we know this is k. And when we multiply this, by 10 to the power 3, this is what we get. We end up getting, this is kilo amperes, right? So we end up getting 42.5173 amperes, right? So this is what we have. Okay. So we have this. Now you're supposed to find the active and the reactive components of the current, right? So when we are doing that, what do we need? We basically know that let's do this. Just remember from how it is given, lagging. Current is lagging, so meaning we have kind of like a resistor and an inductor in the circuit, right? So meaning that somehow, some way, if this is let's see, power here. If this is power, this is reactive power, right? Meaning that we'll have the apparent power here. The same way that will mean that it is specify that. So we assume they are in series. So if they are in series, the currents are the same, right? Yeah, the currents across them are the same. But let's see. We just use this to. We have a what do you call it? Phase angle, right? So let's see. And we don't have the phase angle. We have the power factor. We have cos theta, right? Cos theta, and it was 0.7, right? So let's see. And then we want us to find the active and the reactive component. And we know clearly that if we want to find the, what do you call it? So let's see, current can be here. Let's clean this up. It's still the same thing. So let's see. Current will be here. This is active, right? Current still be here, reactive. And this will be the total current, right? Which is the current in. Yeah. So we can still use this angle here, this phase angle here, right? So let's see. So if we are trying to find this one here, which is the x-axis, that will mean that we use the cos theta. So the active component of the current, just make it the AC. Let's just make it IA. We go to I in, right, cos theta, which is, let's see, let's just write it and then write this again, times the power factor, right? So that will mean that the power in is 42.5173. The power factor is 0.7. So let's see what we have for that. Times, let me just 42.5173, 42.73 times 0.7, right? And that gives us 29.7621. But amperes, the unit very important, amperes, right? Very important. Okay, so we have the active component. Now we need to find the reactive component, right? So let's see. You have to find the reactive component. It basically means that let's just write. Reactive is this is the in, right, times sine theta. Right? But do we have sine theta? Meaning we can't use this particular equation. We don't have the theta, right? But we can use sine. We don't have the theta, right? So the other way to do is that let's look at this again, because they are vectors, right? So we have this, and then this, meaning that we can do some sort of triangle here, right? We can do triangle, and then we can do something related to Pythagoras, right? So that will mean that the equation that we can use is I in squared is equal to I active squared plus I reactive squared. So then I reactive will be square root of I in squared minus I active squared. Right, so that's what we do. So always know what you have and know the equation that you can use. Right, very important. Makes your work easier. So I in is I in 42.5173. So squared 42.5173 squared, right, minus 29. Let's make this bigger. So yeah, the work always becomes easier if you know the equations and you know which ones to use to get what you want, right? So active 29.7621. Square this as well, right? Yeah, so let's see what we get. When it comes to the punching, I always punch it in such a way that if I miss something, the calculator just tells me straightforward I'm missing something instead of missing something and not knowing. So I punch everything before I even put in the values. If you want, you can even use variables, and then you ask the calculator asks you what are the values you want for those variables. Right. See, 42, 5173, 29, 7, 621. This is a minus here. So we get 30.363 30.363 for 40p, right? And there's a way to get the number of decimal places that you want. So 30.3634 is current. So what? Amperes, right? Amperes. Unit very important. Unit very important. Unit very important. Okay. So now we saw that as well. So what are we trying to find now? Trying to find the reactive kVAR, right? Then again, they didn't specify whether the input or output. So let's see. Let's see what we can do. Reactive kVAR. So this basically means apparent, right? Apparent power, right? Apparent power is composed of the active and the reactive, right? And which ones do we have, right? It's the input that we have, right? So we have the input power. Let's see. We have the input power, right? And then we can get the input reactive power as well. So that will mean that clearly the one that we are trying to find here, this one is so the reactive kVAR. Minutes reactive. The reactive kVAR. Okay, so that means we are looking for the reactive power, right? There's a reactive power. Let's see. Trying to look at all the values that they've given us as in within the question to see what we are looking for. Okay, so let's see. So if we were to look at only the unit, we would have said that we are just looking for apparent power, right? But then said reactive. So that will mean that there's an R here that has not been stated but has been placed here, right? So reactive power. Okay, so let's see. So which power do we have? The input or output channel we have. We basically have the apparent power, we have the input, right? So if we are trying to, let's see, we are looking for here, right? We don't know that. This is the right. But then do we have S input? So let's see. Yeah, we have S input. Yeah, we checked for that. We have X input. Where's that? Yeah, we have S input, right? Okay. So that will mean that in order to find the reactive input power, that will be, let's see, you can do this, and then if you have the, what do you call it, the angle, you do, what's the name, sine theta. But then again, we don't have the angle directly, right? You can find if you want. Yeah, but there are a lot of equations that you can use. A lot of equations that you can still use because it's reactive here, right? And there are, let's see, you can use the voltage, right? And then you can use the reactive current, right, to find it. Yep. Yeah. Right. So let's see, which one should we do first? Let's do the this one first. This one. So we know that the voltage is 400, right? And the input reactive current is 30.3634. Let's see, 400 times 30.3634, and that gives us, let's see, 121 points. That gives us 12145.36, right? 136. Right. So we can do some parentheses. Sorry, so 1, 2, 3. So that'll give us 12.145. Let's do 4 dp. 4. Right, and because we are doing reactive power, that will be what? VAR. Right. So let's see if we can use the input power and then this one to find it. Right. Okay, let's see. Because we don't have this theta directly, we can't use it directly, right? But we know that this Q again is also the same as if you have, let's see, let's write the equation now. So if we have, basically start from this one. We have S squared is equal to P squared plus Q squared. That's for the RMS values, right? And then this right here, we have the S in, we have the P in, and then because of what we have, we can basically look for the Q in, right? It didn't specify, so that's what we are using. Okay, so then yeah, you can use this one as well. So I mean that Q in will be the same as let's see, square root, right? Square root, we have S in squared minus P in squared, right? So let's see what we get for that as well. Okay, so that will mean we have square root of S in was, I think, 17 point something. Is it S in? Yeah, so 17.0069 kilo. So 17.000069 kilo. And when we attach that kilo, 10 to the power 3, let's see, the dot moves from here to 1, 2, 3, right? So the dot ends up here. We've introduced a kilo. Okay. Squared, and the P in, what do we have? P in, that's the power, active power input, right? Found that to be 11.9048. So if we move it 1, 2, 3, right? So we have 11904.8, right? So we have 1. Let's bring this here. Okay, 11904.8 squared, right? Okay. So now let's see what we get. We have square roots. We have 1700.6.9 squared minus 1190.4.8 squared, right? So let's see. If I even use the values there so that the end result I'll get to be in case, right? So let's see. It gives us, let's see, that's 12145 12145.3853, right? We also are looking for reactive, that's VAR, right? And then we want to do some processes, 1, 2, 3. The same thing, it gives us a 12.145. Let's do 4 dp, 4853 kilo VAR. We need very important, kilo VAR. Right. So the same thing as we had here. Right? This should go out. Yeah. Depends on the DP, the number of DPs that I want to do. 1, 2, 3, 4. Let's see. This turns to 2. Yeah. So you see, very close. The values are almost the same. Yeah. So that's it. Right. So let's see if we have anything else to solve. Yeah. So that was the last time, trying to find the active and reactive components of the current. The C is just the reactive component. Yeah, that's reactive kVA. Right? So they even specify that they want to see the key. So it's very important to pay attention to the request of the question or the problem. Right? So we have the key, we have the VAR. Yeah, so that's it.